Okay, so this is another video in the series from Math 1224 for UTSA. Today we'll be talking about 3.7 improper integrals. There are two types of improper integrals, two main types. Type 1 is where you are finding the area under a curve from some starting point we'll call A, just out to infinity. And you can see why that would be weird. Like, where do you stop? Where does the definite integral stop? And then type 1, well, this would be where you're going from some asymptote up to A. So basically, if our function's f, then this would look like, say, the integral from A to infinity of f of x dx. And this is called improper because this is not a definite integral. You don't have some ending point for the integral. And then type 2 would look like this, where you would have an integral from, say, 0 to a in this case of f of x dx. And the weird part about that is, well, this doesn't really work because the function's not defined at 0 because there's an asymptote there. So how would you do that? And basically, in the first case, you would find the limit. You would say, oh, let's just do the integral from, say, a to, I don't know, t. We'll mark t right here, right? So this will be the limit as, say, t goes to infinity of the integral from a to t of f of x dx. We have room here, right? And then for this one, we could say, I don't want to use t again, but we could use, I don't know, v, just to pick a different letter, right? And then we could say, oh, well, this is going to be the limit as v goes to 0 from the right of the integral from v to a of f of x dx. And in both cases, the limit may or may not exist. It depends. So when the limit exists, we'll say that the integral converges and you get some number. And if the limit does not exist, we'll say that the integral diverges and we don't get anything. Okay, so let's go look at our first example. And I'm not always going to draw these out. Sometimes I will, sometimes I won't. It depends. So for this one, I'm not going to bother drawing anything, but I am going to liken it to, this is a type 1 example, right? We're going out to infinity, that's type 1. So this equals the limit as, say, t goes to infinity, right? Of the integral from 1 to t of, let's write this as x to the negative 2 power, rather, dx, okay? So now I can focus on, well, what is this definite integral evaluated, because, if t is like 10 or 100 or 1,000, well, then you can find the definite integral, right? And we'll do the limit afterward. So I can just find this antiderivative. So this will be the limit as t goes to infinity, let's say of negative x to the negative 1 power, right? Evaluated at 1 and at t. So this will be the limit as t goes to infinity of, say, negative 1 over t minus negative 1 over 1, right? When I evaluate the antiderivative at the two endpoints. So this is the limit as t goes to infinity of negative 1 over t plus 1. Now, as t goes to infinity, this first term, this is going to go to 0, right? So therefore, I'll get 0 plus 1, which equals 1. So we'll say in this case that the integral converges to 1. Okay, so that is the value of the integral. 1, the area is 1, basically. The area under that curve from 1 to infinity is 1, which seems kind of weird. If you're going out to infinity, how would that be possible? But basically, taking this graph as an example, what that means is that the you have a horizontal asymptote, right? And although there's, quite a lot of vertical space here between the graph and the x-axis, as you go out further to the right, this is not maybe drawn to suggest what I'm about to say, but the gap here, the distance of the graph from the graph to the asymptote will shrink and get smaller and smaller and smaller. And if this gap shrinks fast enough, then the area can be total. Like the rectangles can be added up in the Riemann sum, and you get a total essentially. If the height shrinks fast enough, if the graph approaches the asymptote quickly enough, then you get a total. And if it doesn't, well, then you don't, and it just depends. So now I think the next one is a type 2, I believe. Yeah, let's do the type 2 for this same function, 1 over x squared. So for this one, I'm going to say that I want to find the limit. Oops, let's write that neatly. The limit as, I don't have to use v. I can use whatever letter, but I'll use v since I've already kind of committed to that. The letter used doesn't matter. Limit as v goes to 0 from the right, okay, of the integral from v to 1 of x to the negative 2 power dx. And of course, this antiderivative we've already found, but I'll just go ahead and go through the steps anyway. So the limit as v goes to 0 from the right of negative x to the negative 1, evaluated at v and at 1. Okay, so this will equal the limit as v goes to 0 from the right of, well, that's going to be negative 1 over 1, right? Minus negative 1 over v. Okay, so this will equal the limit as v goes to 0 from the right of negative 1 plus 1 over v. Okay. Now this might not be so obvious. Like how do I deal with this? But if you think back to Cal 1 and think about the graph of y equals 1 over x, you know, it's a hyperbola, right? Basically, I'll do a quick sketch over here of what y equals 1 over x looks like. Y equals 1 over x. It's not very good x, but we'll go with it. Looks kind of like this in the first quadrant, and I guess I'll do this quadrant 3 as well. So something like that, right? Something like that. So as we approach 0 from the right, we are following the graph like this, and we're going up. So we get infinity, right? That's the limit. So, and then plus negative 1. Of course, we don't talk about having, we're going to have infinity plus negative 1, but if one term goes to infinity, then this numerical value here doesn't really matter. If we really wanted to, we could get a common denominator and combine like terms and go that direction, but we don't need to do that. This goes to infinity, so this diverges. So we'll say this limit equals infinity. The integral diverges. Diverges. And specifically, this diverges to infinity. Because you could have divergence to negative infinity. If you had negative values, then you could have that as well. Okay, next example. So this is a type 2 example where we have an asymptote, right? If you plug in 2 into the function, you get 4 minus 4 on bottom, you get 0. So that doesn't work, right? The graph of this, I'll do a quick sketch, not meaning to be super accurate, but just kind of roughly. If you think about the denominator, just the graph of the denominator on its own, it kind of would be a semicircle, the top half of a circle if you graph just like y equals the square root of 4 minus x squared. And that's what you would get if you did that. Let me make sure these look like asymptotes. Okay, so the graph looks a little bit like, if you plug in 0, you get 1/2 as a result. So the graph kind of looks like a parabola that's trapped between two asymptotes. It looks a little bit like that. So we're being asked to try to find this area, the integral from 0 to 2, right? So something like this is what we're looking for, and that may or may not be finite. Is that a finite amount? Like, is it 10 or whatever, or is it infinite? You can't get a value. Well, let's do a limit. So the limit, say as I don't know, I'll use t in this case. So t is somewhere here, and t is going to approach the asymptote. So we're going to be finding this area. right here from 0 to t, okay? And then we'll do the limit afterward to see if we get something that way. So the limit as t goes to 2 from the left, right, of the integral from 0 to t of 1 over the square root of 4 minus x squared dx. Okay, so how are we going to do this? There's a couple ways to get started. Depending on how you learned this in Cal 1, you might go, oh yeah, I have a formula for that. Perhaps not. So I'm going to try to do this as simply as, well, you might notice that we could do a trig substitution of the form, say, x equals sine theta or a sine theta. That's an option, but I think what might be easier is just to do the following. Let's say that x equals 2u. Okay, that'll make things a little bit easier, I think. So then dx, is that what I want? Yes, dx equals 2 du. Okay, so this equals the limit as t goes to 2 from the left of let's say 0, and is that going to be 1/2 now? I'm sorry, it's going to be t over 2, right? If you take t, because we're doing a change of variables, so I have to change my limits of integration. If you plug t in for x, then u would be equal to 1/2 t, or t over 2. So 0 and t over 2. Okay, those are my new limits. And then I get 1 over the square root of 4 minus 4u squared times 2 du. Okay, so that's going to equal the limit. Oops, let's write that neatly. The limit as t goes to 2 from the left of the integral from 0 to t over 2 of 1 over, and I notice that I can factor out these 4s and move them in front of the root, and when I factor out 4, I'll have the square root of 4 times in parentheses 1 minus u squared, and then the 4 can move out of the root and become a 2. I'll do all that in one step. Hopefully that's clear to everyone. Okay, and then 2 times 2 du, so now I get some cancellation, right? These 2's cancel. So I get the limit as t goes to 2 from the left of the integral from 0 to t over 2 of 1 over the square root of 1 minus u squared, and that is one where you might notice, oh yeah, that I recognize this expression, this integrand, as the derivative of sine inverse of u. So we don't need a trig substitution. You can do that, but since this is pretty straightforwardly, at least somewhat, to just be the derivative of sine inverse, well, then I don't need to go through all that trouble. So this will equal more horizontal. We have plenty of vertical room, I think, but I'm going to start using horizontal. Room because I don't want all this to go off screen too quickly. So limit. So t goes to 2 from the left of sine inverse of u evaluated at 0 and at t over 2. Okay, so then this is going to be the limit as t goes to 2 from the left of sine inverse of t over 2, or t 1/2 t if you want, minus sine inverse of u, 0 rather, which of course is 0. So at this point, how you deal with this depends on a few things. You could think, well, can I just plug in? Can I just plug that in? Does that work? Is sine inverse continuous? Is this in the domain? Well, yeah, if you take the standard inverse sine function, the domain would be -1 to 1, but this is t over 2, okay? So, how do I want to do this? Yeah, so if you have, let's change colors here. If you have sine inverse of, let's say, u, right? Sine inverse of u, well, then u is between -1 and +1, right? But if you have sine inverse of t over 2, well, that means that t over 2 is between 1 and -1. So if I take this inequality and double everything, multiply 3, or sorry, not 3, but 2 on all 3 components, I get -2 is less than or equal to t, which is less than or equal to 2. So if we're approaching t from the left, and part of the domain of that function is that t is less than 2, well, then 2 is in the domain, right? Just plug it in. So I said less than or equal to, of course. So I just plug it in because that's in the domain. So this is going to be sine inverse of 1, right? 2 over 2 is 1 minus 0. Sine inverse of 1 is pi over 2. And there we go. That is the value of that area. Again, this was a type 2 definite integral, or improper integral, I should say. So we had to think about the asymptote. We had to think about the substitution we're doing. And then also think about, okay, is this in the domain? Can we just plug this in? Because we are doing a limit. And with limits, you have to be careful not to try plugging in values that are not acceptable to the function. Okay, so let's do another type 1 improper integral. So integral from 1 to infinity of 1 over x dx. I'm going to do a quick sketch. I won't always draw these out, but for the first few I will. The graph here is fairly similar to the first example. So let's do a rough sketch. Won't worry too much about being accurate. That's good enough. Not very good, but good enough. And I'll do quadrant 3 as well, even though we don't really need it. Okay, so here's 1. Right? And we want the area under this graph out to infinity, right? But of course, that's not a definite integral because that is not a closed interval from a to b. So we're going to pick a location and say, oh, let's call this t. I typically use t, but the letter doesn't matter. And we'll find this area, and then we'll find the limit of that area as t goes to infinity. So this equals the limit as t goes to infinity of the integral from 1 to t of x to the negative 1 power dx. Okay, so if you think about, oh, well, what is that antiderivative? Well, that's going to be the natural log of the absolute value of t. So this equals the limit as t goes to infinity of ln of x evaluated at 1 and at t. So this equals the limit as t goes to infinity of ln of t minus ln of 1, which of course is 0, right? So this essentially turns out to be what's the limit as t goes to infinity of ln of t. Okay, and just think about the graph. What does the graph of ln of t look like? Well, you probably know, but just in case, I will do a quick sketch. Again, probably will not be that good, but we'll go with it. Be good enough. And you might recall that the range of the natural log function is all real numbers. As you follow the graph out to the right, it goes up and up and up. Now it does so slowly. The y-coordinate increases slowly, but it does cover infinity. So this is infinity. So this integral does not converge. This diverges. Diverges to infinity, which might seem kind of weird because the first example we did, no, we got convergence. We got a number, right? Why is this one different? Well, this is sort of an iconic example that's going to come up again later where this function just barely fails to converge. It almost does. It just doesn't quite make it. Barely fails to converge. And we'll see more on this later in a later chapter. Okay, so we saw earlier that if we found the integral from 1 to infinity of 1 over x squared dx, we got a number. We got 1, I think. And then if we look for the integral from 1 to infinity of 1 over x with an exponent of 1, right, dx, then we get nothing. It diverges. We don't get a result. So what if we say, well, leave the exponent as a parameter. So we'll say p is greater than 0. Let's look for the integral from 1 to infinity of 1 over x to the p power dx. So basically, we will have a graph a little bit like this, where we're going to find the area from 1 to t, and then let t go to infinity and see what happens as a result. Okay, so let's say the area, this is going to be the integral from 1 to t of x to the negative p power dx. Okay, so this equals x over negative p plus 1 over negative p plus 1, okay, evaluated at 1 and at t. So this equals t, and in the exponent, I don't have to write this as negative p plus 1. I can write it as 1 minus p if I want. That's optional. So 1 minus p over 1 minus p minus 1 to the 1 minus p power over 1 minus p. Okay, so this equals, in fact, I can do a little bit of factoring if I like. I have options here. I'm going to factor out the 1 minus p, put that in front. 1 over 1 minus p, okay, times t to the 1 minus p power minus 1, okay? So, if p equals 1, well, then this doesn't exist because you can't divide by 0. So the integral diverges. It doesn't exist. We don't get anything. If p is less than 1, okay, well then the area we're looking for, the integral from 1 to infinity, well, of 1 over x to the p dx, well, then this is going to equal the limit as t goes to infinity of 1 over 1 minus p times t to the 1 minus p minus 1 power. Well, t to the 1 minus p power minus 1, okay? So what is that limit? Well, we can put the 1 over 1 minus p out in front, okay? Because that's, the p is a parameter, the limit does not see it as a variable, so limit as t goes to infinity of t to the 1 minus p power minus 1. Now, if p is less than 1, p is small, okay? That means that this exponent is greater than 0. So we have t with an exponent of greater than 0, right? And t is going to infinity. Well, then this diverges. This goes to infinity, right? Because the exponent is positive. So this would equal infinity. We get divergence. Or I'll just write divergence because I'm out of horizontal room there. However, if p is greater than 1, then the integral from 1 to infinity of 1 over x to the p power dx equals 1 over 1 minus p times the limit as t goes to infinity of t to the 1 minus p power minus 1. Now, remember, if p is greater than 1, well, that means this exponent is negative. So we'll have t going to infinity with a negative exponent, which goes to 0. So this will equal 1 over 1 minus p times negative 1. 0 minus 1 is negative 1, of course. So you get 1 over p minus 1. So we only get convergence if we get this value because we have p is greater than 1, right? So basically, the integral from 1 to infinity of 1 over x to the p power dx, well, equals either infinity, right? And this is if p is less than or equal to 1, right? P is already positive, but less than or equal to 1. And then we get 1 over p minus 1 if p is greater than 1. Okay, and this will be true in general for any p value. So if you want to know, well, what about 1 over x cubed or 1 over x to the 5th or whatever, this formula will always work. Okay, so brief review of the comparison test from Cal 1. So if you've got two functions f and g such that f of x is less than or equal to g of x on some interval from a to b, okay, then the integral from a to b of f of x dx will be less than or equal to the integral from a to b of g of x dx. You know, basically, if you've got two functions, let's say we got like this. We got vertical axis, horizontal axis. If the auto line tool will work with me, horizontal axis. There we go. So here's A, here's B, right? You got two functions. Here's G and here's F, right? the area under f from a to b will be less than or equal to the area under g from a to b, provided the function f is less than or equal to the function g at every point, right? One is below the other, then the integrals are ordered that way. Okay, hopefully that makes sense. That's from Cal 1. So the comparison test is similar to this, similar concept. So given two functions, f and g, such that f of x is less than or equal to g of x on the interval from a to infinity, so we're looking at an improper type 1 integral, okay? This is also relevant to type 2 integrals, but we'll end up not using this for type 2 integrals, only for type 1, at least in the future chapters. A homework problem might involve this, but you apply this same concept. So if the lesser function has a divergent integral, then the greater one would have to as well. Okay, if the integral from a to infinity of f of x dx diverges, okay, it's the lesser one. It's the one that is a lesser value, and it diverges to infinity. And let's say specifically to infinity. I think we should do that to infinity. Then, so does the integral from a to infinity of g of x dx. It has a greater value, so it would have to also diverge. There's more area, right? Reversing that, if the integral from a to infinity of the larger function, the greater value function, right, converges, so the area is a finite number you can calculate, well, then the lesser function would have to do that as well. Then so does the integral from a to infinity of f of x dx. Okay, so this is similar in concept to the comparison theorem from Cal 1. Same idea. The lesser function has a lesser area under it. So if you show that this lesser function is divergent, well, then the greater function must also be divergent without a direct calculation. Okay, and then if the greater function is convergent, then so is the lesser function without direct calculation. And this is useful because some functions are really hard to deal with. Others are easier to deal with. So that's just the purpose of this comparison. So let's look at using this in an example. Let's say I had this function, integral from 2 to infinity, or this integral rather, integral from 2 to infinity of x dx. And then you go, well, that's pretty obvious. I can just draw it and look at it. But let's not do that just now. Let's say, well, can I compare this to anything, right? So I could say, well, you know what? I'm pretty sure that the function x is greater than or equal to 1 over x, which we've already shown is divergent, right? I'm pretty sure that this is always true for any x on this interval from 2 to infinity. Well, is it? Let's confirm. If I take this and I'm going to multiply on x, by x on both sides, so x squared is greater than or equal to 1. And I have to think, okay, is this a valid algebra step? Can I multiply x on both sides? Well, of course, x is a number. X is a positive number. So I don't have to switch the inequality direction, right? That's an important thing to think about. If you have negative values potentially, right? If this interval were different, I have to think, well, does the inequality change direction? In this case, it does not. So I can do that. It's valid algebra. Is this always true? Well, if x is greater than or equal to 2, like it's 2 or 3 or 1,000, well then yeah. So yes, this is always true, okay? So that means that this is always true. So this thing is going to have to be greater than or equal to the integral from 2 to infinity of 1 over x dx. And I hear you saying, well, but wait a minute, this is not 1, this is 2. Well, if we went and did all of the work again, then yeah, that would happen. Basically, this reasoning holds. If we take that function that we already worked out, we worked out the integral from 1 to infinity, diverges, right? So here's our function. And we said, okay, from 1 to infinity, this area is infinitely much, right? You can't total it up. There's too much stuff there to total it. Well, if you chop off this beginning part and throw it away, does that suddenly become finite? Well, no. You're chopping off a finite chunk of an infinite piece. The rest is still infinite. So this diverges. This equals infinity. So that means that this must diverge. Okay. Sometimes we have to use this reasoning where if you chop out a piece that's clearly a definite integral from 1 to 2. That's clearly a definite integral. And I know that the rest is still divergent. That's reasoning we're going to have to use from time to time. Okay, so what about an example where it's not so clear? If you look at the graph of this guy, okay, and I'll do a quick sketch as I do, and it will not be perfect, but we will go for pretty good. You probably have seen this before. This is often well, you might not have, but this is covered in stats courses sometimes. This is a bell curve, so you've probably seen the graph at some point, something like that. That's pretty bad, but whatever. We're worried about quadrant 1 anyway. So is this, is this a finite amount? Can we calculate this, that area, right? Well, basically I need to try and make a comparison. So if I have an intuition that it's not convergent, then I want to compare it to something that I know is not convergent, and therefore I can show, well, this is I'm comparing it to a thing that's divergent. I show it's bigger, therefore it has to be divergent as well. If I have a feeling that it's probably convergent, I want to compare it to something that I know is convergent and say, well, because I've compared this thing as convergent and shown that the present example is smaller than that convergent thing, now I've shown that my present example is convergent. So let's start by considering, well, what if this may be divergent? I'm pretty sure it's convergent. I've done this example before, but I don't have those notes right in front of me, so I'm not just looking at something saying, oh yeah, it's convergent because I worked it out earlier. I did, but I'm not looking at it right now, and I worked it out like a year ago, so I don't recall right now the exact details. Anyway, what if I wanted to compare this to 1 over x? We know that the integral from 1 to infinity of 1 over x is divergent. And again, if I were to go here and say, well, let me chop out this part up to 1 and ignore this part, chopping out a finite chunk is not going to suddenly turn an infinite value into a finite value. That's not going to happen. So I can make a comparison to 1 over x if I want to. Basically, I could say, well, this is approximately the integral from 1 to infinity of e to the negative x squared. It's off by a little bit, but approximately, right? It's a lot of rounding there, potentially. A lot of rounding. But we're asking, is it convergent or not? We don't care. Well, is the value 10 or 10 trillion? I don't care. Is it convergent? That's what we care about right now. So we can fudge a little bit on where we start the integral because it's not an asymptote or anything. If there was an asymptote, well, you can't do that. But if it's not an asymptote, if you're cutting out a chunk that is definitely in the domain of the function with no asymptotes, then you're not going to disturb convergent or not convergent by doing that. Okay. So let's compare this to 1 over x. I would like to show that this is greater than 1 over x. Okay. Because if it is, well, then I can say, oh, that this is definitely divergent because it's greater than this other thing that I know is divergent. So I'm going to start by utilizing the fact that I have a minus sign here and rewrite this left-hand side. Oh, this is 1 over e to the x squared greater than 1 over x. And this greater than comes with a question mark because this is uncertain. We're trying to demonstrate this. I want to, through a couple of algebra steps somewhere down the line, get something that's clearly true, and then work back, oh, therefore this is true, okay? So what I can do, and keep in mind, in our interval, we only have positive values, so we don't have to worry too much about inequalities switching. I'm going to basically flip both sides, and when you flip both sides, you switch the order of the inequality, not because there's a negative involved, but, if you have 1/2, that's greater than 1/3, right? So if you flip both sides 2 and 3, well, the 3 is greater. The inequality switches directions when you form the reciprocal on both sides. Okay, so e to the x squared less than x, question mark? If you look at that and think about it, well, no. If you even put in a 2 or a 5, right? E to the 25th power is less than 5? No, of course not. No, that's not true, right? So I've already just found an example where this does not work. So that's just not true. It's something I can attempt to show it. So how about this? And I could come up with other examples, other things that I know are divergent and compare to that. But it turns out this one is convergent. So let's cut to the chase and attempt something that would actually get that result. When you're doing one of these, like for the homework, you don't know up front which one it is necessarily. So you just have to start with something. So your first guess might be totally wrong. And so you're trying to do algebra that is not going to work anyway, but you don't know that till you try. So don't worry about having to try 2 or 3 different things, or 4 perhaps, or maybe more. When you're doing one of these, that's just a possibility, and it's okay. So let's try comparing this to x squared, rather 1 over x squared, I mean to say. Okay, now because I know that 1 over x squared, the integral from 1 to infinity of 1 over x squared dx, that's convergent, right? Because this is the example of having 1 over x to the p power, and p is greater than 1 in this case. I want to show that this is less, because then I know this is convergent. So if I show that this is less, then I will know that this is convergent as well. Okay, and again, we are thinking about the interval from 1 to infinity because this has an asymptote at 0, so that's basically what we're doing. Okay. So again, I'm going to start by utilizing this negative exponent to rewrite this as 1 over e to the x squared. Okay, less than 1 over x squared. I can again flip both sides, so e to the x squared is greater than x squared. And I look at that and I go, you know what? That seems right. If I say x equals 1, right? If x equals 1, well, then I'd have e to the 1 is greater than 1. Yeah, that checks out. What about x is equal to, I don't know, 5? Well, then e to the 25th power is greater than 25. Well, yeah, that's definitely true, right? E to the 25th power is a huge number. How do I know that this is always true? You could think about the graphs maybe, right? We know what the parabola y equals x squared looks like. Do we know what y equals e to the x squared looks like? So one thing we can do is the following. And how much detail you do on this depends on how important it is that you're sure, but when you're talking about testing for convergence or not, you need to demonstrate. Like, how do you know this is always true? Through these checked numbers, I can go, I'm pretty sure it's true, but how do you know? Okay. So what I'll say is this. If we think about, say, f of x equals e to the x squared power, right? And g of x equals x squared. I can think about h of x, the difference of the two. So e to the x squared minus x squared, the difference between the two. And I can think about the derivative. Okay, we're thinking back to Cal 1. We're going to think about the derivative telling us about the function increasing or decreasing. So at h prime squared, this is going to be 2x e to the x squared minus 2x, right? And I think about, when is this function increasing and decreasing? Okay, and I'll point out now, I could have said it earlier, but I'll point out now, this function gives you the difference between these two, right? I've subtracted them. So this function is positive when f is more than g, and this function is negative when f is less than g. This function increases when g becomes further from g, larger but further, larger by a greater amount, let's say. The difference increases, right? And then this function h decreases when the difference is decreasing. The two functions are getting closer together in the graph. So when is this derivative 0? When are the functions not, as you move from left to right on the graph, when are they not getting closer together or further apart? Well, if I look for where this is 0, I can say, oh, well, 2x e to the x squared minus 2x. I can factor 2x out. So 2x times e to the x squared minus 1, right? So 0 equals 2x, or 0 equals e to the x squared minus 1. So 0 equals x, or 1 equals e to the x squared. And how do we solve this equation? Well, you might look at it and go, well, if you plug in 0, that solves it, which that's the only solution. So x equals 0. In either case, x equals 0 is the only place at which the derivative is 0, non-increasing, non-decreasing. Well, x equals 0 is not in the interval that we're thinking about. So these functions are never just sort of steady state equal distance from each other. When is this function positive? Well, if we do sort of like a first derivative test thing, I can make a number line. Say, okay, 0 is our only critical number, right, for h, right? H of x equals e to the x, equals e to the x squared minus x squared. So on this entire interval, either this function is only increasing or only decreasing, right? You can't do anything else. So how about at 1? Is the function increasing or decreasing? Well, h prime of 1, right? This is going to be 2 times 1 times e to the 1 squared power minus 2 times 1. So 2e minus 2. Hey, that is positive. This function is only increasing on that interval. So the difference between the two functions only increases as you go from left to right on the graph. So this is always true. It's true when x is 1, it's true when x is 5. And because of this reasoning here, it's always true. So I kind of have to resort to the first derivative test. Not for local min max, but I should call this the increasing decreasing test. I'm doing the first phase of the first derivative test for local extrema. Is the function increasing or decreasing on the interval that I care about? And from 1 to infinity, the function only increases. So this inequality is always true. So yep, always true. So I can say that because through the comparison test, this is convergent. Okay, so since e to the negative x squared power is less than 1 over x squared for all x greater than or equal to 1, by the comparison test, the integral from 0 to infinity of e to the negative x squared power dx converges. What does it converge to? Well, that's a bit harder. Next example. My recollection for this one, this is me remembering, is the square root of pi over 2. I think it's either the square root of pi or it's the square root of pi over 2. I forget which one of those it is, but it's something along those lines. I don't recall right now the exact value. Anyway, this method doesn't help you find the value. For that, you need stuff from Cal 3. But it does let you confirm, oh, this definitely converges. This is a number. Why would you want to do that? Well, how about before you go through all the trouble of trying to actually pin down the value, you can confirm that there's a value to find at all, because you certainly would not want to start leveraging a bunch of Cal 3 and then get nowhere with it because it doesn't work because you forgot to use Cal 2 to check, is there even a number to get? Okay, so now we're going to do an example that I really enjoy. I've got the graph of y equals 1 over x on the interval 1 to infinity. Well, drawn up to 5, but the domain is 1 to infinity. Obviously, we can't draw all of that. And I'm going to draw out what Gabriel's horn looks like. And it's, to the best of my ability, or to the best of my ability to manage the interface here. There we go. That's better. Okay. So basically, if you were to revolve that graph around the x-axis, right? And then I would have something like that. Good enough, fine. So that's Gabriel's horn, and it goes out to infinity, right? Pretend I drew that better, right? So the neat thing about Gabriel's horn, it's like a funnel that never ends, right? The neat thing is, I guess I'll tell you up front that there's a very surprising seeming contradiction when you calculate the volume and when you calculate the surface area. So let's do volume first. So for volume, we're just going to basically be able to use the disk method, right? If I think about taking a slice of, well, that was interesting. Think about taking a rectangle here, right? And then revolving that around to use the disk method. So something like, I guess I could take this, duplicate it, oops, put that here, do that, something like that, duplicate it, like that, right? And get a disk that way. Okay. Then the thickness of the disk, of course, is dx, right? And the radius of the disk, let's change colors here. The radius of the disk is, of course, 1 over x, right? Then all we got to do is say, oh, well, let's say that the area of the front of the disk, right? This is going to be pi r squared. So this is pi times 1 over x squared, right? There's your first hint. And so then the volume, or dv in other words, this is going to be pi times 1 over x squared dx, right? Okay, so down here we can say, oh, well, that means that the volume of Gabriel's horn is going to be v equals the integral from 1 to infinity, right, of pi times 1 over x squared dx. Well, if I factor the pi out, integral from 1 to infinity of 1 over x squared dx. I'm pretty sure we already worked that out. That integral is 1, so pi times 1, which is, of course, pi. So there you go. That is the volume of Gabriel's horn. Okay, it's like a funnel with no end, but you could fill it up with a finite amount of stuff. You could pour pi units of water into it, and there you go. That's pi cubic units of water, and there you go. It's full. It's a funnel, but you can fill it. Okay, so let's do the surface area now. So for surface area, we're going to need to use this formula, the integral from 1 to infinity of 2 pi y ds. So this will be the integral from 1 to infinity of 2 pi times, well, 1 over x, okay, times the square root of 1 minus, plus dy dx squared, right, dx. Okay, well, what is dy dx squared? Well, let's go back up here. dy dx is going to be, well, negative 1 over x squared, right? So if we square that, dy dx squared, we get 1 over x to the 4th. Okay, so come back down here. This is the integral, and I'll put it here, I guess. The integral from 1, and I'll put the 2 pi out in front. That's fine. Integral from 1 to infinity of 1 over x times the square root of 1 plus 1 over x to the 4th dx. Okay, now pause the video and think, what do you make of that? How are we gonna evaluate this? Like, supposing we said, oh, well, let's do the integral from 1 to t, and then we'll do the limit afterward. How would you even do that? Well, it turns out we don't need to, because it's not too hard to show that 1 over x times the square root of 1 plus 1 over x to the 4th, this is greater than 1 over x for all x greater than 1. When x is greater than or equal to 1. So if you think about it, if I multiply both sides by x, I'll get the square root of 1 plus 1 over x to the 4th. It's greater than 1. So if you take 1 and add a small amount to it, right? So 1 plus something, and then find the square root. Is the result always greater than 1? In other words, if I square both sides here, 1 plus 1 over x to the 4th is greater than 1 squared, which is 1. Or in other words, subtract 1 on both sides. Yeah, that is always true. Remember, x goes from 1 to infinity. So 1 over x to the 4th is always positive because x is positive, and it's to the 4th power. So how could that be negative? It couldn't even be equal to 0, right? So this equals infinity, diverges. Okay, so what we get is the following. This shape, Gabriel's horn, is one in which the volume is finite and not even very big, right? The volume is pi. It's a small number, right? But the surface area is infinite. So in other words, if you were holding Gabriel's funnel and you had a bunch of paint, you could not paint the outside of it. You would not be able to get enough paint. And you'd start painting down the funnel, right? You start at the top, start painting down the funnel. You would never finish. You would run out of paint. But if you just poured the paint in, it would fill it easily. So it's an interesting shape. And this is an interesting, maybe not technically practical usage of this technique, but it's an interesting usage of this technique. Okay, so let's switch back to doing type 2 improper integrals. So we had previously worked out for type 1 integrals from say 1 to infinity of 1 over x to the p power dx, that those we determined the conditions under which those would be convergent or divergent. And the reason we spent the time to do that is that we're going to need to use that technique, that formula later. For type 2 improper integrals, we're not going to reuse them later, at least not often. So we don't need to work this out. Oh, what about 1 over x to the p? How does that work? We're not going to bother with that. We're just going to do a couple of examples of how do you calculate it without a formula. So for this one, I basically am going to say that, I know I have an asymptote at 0, right? So in other words, quick sketch here. In other words, the graph of this thing, and notice that the domain is 0 to infinity. There's no graph in quadrant 2 or quadrant 3. Something like that. Yeah, let's go with that. So we want the integral from 0 to 1. So here's 1. And then again, we'll say, oh, well, here's t, right? And then we'll find the area from t to 1, and then we'll let t go to 0 and see what happens. Okay, so this will be the limit as t goes to 0 from the right of the integral from t to 1 of x to the negative 1/2 power dx. Okay, so this is going to equal the limit as t goes to 0 from the right of, well, is that 2? Yeah, 2x to the 1/2 power, evaluated at t and at 1. So this equals the limit as t goes to 0 from the right of, well, 2 minus 2 times the square root of t. Okay, now since t is going to 0, well, that's in the domain there, so let's just plug it in. 2 minus 2 times square root of 0, we get 2. So this one does exist. So when this might suggest something to you, that when p is less than 1, right here, p is 1/2, maybe, the type 2 integrals are always going to exist. There's probably a formula we could work out, but we're not going to need it later, so we're not going to bother doing that at this point. Okay, so this is similar. It's another type 2 example, and for this one, do another quick sketch. And this one, since p is odd, there's graph both in quadrant 1 and quadrant 3. I'm not trying to be accurate with this. I'm just trying to get the graph basically done. The shape really, it should be skewed much more like that. Oh, well, like that, but much more like that. But I'm not going to worry about it. It doesn't need to be super accurate. So we're again going to say, okay, from 0 to 1, that's the area we care about. We're going to again put t somewhere here, and then we will find the definite integral, and then let t go to 0, and then we'll see what happens. Okay. So this is the integral, or rather the limit as t goes to 0 from the right of the integral from t to 1 of x to the negative 7th power dx. So this equals the limit as t goes to 0 from the right of, well, let's say x to the negative 6th power over negative 6, evaluated at t and at 1, right? So this will be the limit as t goes to 0 from the right of, well, 1 over negative 6, so negative 1 over 6, right? Minus, which I guess I could count as a double negative, but I'll do that afterwards. So minus t to the negative 6th power over negative 6. So this equals the limit as t goes to 0 from the right. That's pretty bad, 0. Let's fix that. 0 from the right of negative 1 over 6 plus 1 over 6t to the 6th power. Okay. Now, since t is going to 0, I can look at this and go, well, thinking about the graph of 1 over 6t to the 6th, I can say, well, yeah, that's not defined. This diverges. Yeah, so this is going to equal infinity, right? Diverges. Right?